All right, gang. Second uh, video, easy for you to say, right? Second video on testing theory, looking at measurement, validity, and reliability. We're still going to be focusing on reliability. We're going to bring in a pretty cool concept here, something called classical test score theory. So I'll try to make it not boring, but no promises. I can't dance, I can't sing, so I really don't know what I can do to entertain you. This stuff's going to get really cool once we start looking at exams and start calculating reliability, get into factor analysis and rotations and all the sort of cool stuff. But we've got to have some foundation to expand on this dialogue. So that's the purpose of the first four videos, is just to set the foundation for some bigger, better, cooler stuff. All right, gang, reliability. Let's talk a little bit about it as we looked, or at least saw in the previous video. It's an instrument, or I should say the reliability of a test is just concerned with consistency. Wouldn't you know it, I start talking, the dog wants out. Hold on. Oh, that's hilarious. I think what it is, I think my dog is just, my dog's lazy. My dog's old. So she hangs out on the couch a lot throughout the day. And typically it's pretty quiet because I'm working on stuff and putting up lectures, or not putting up lectures, but preparing lectures. And I don't really make a lot of noise when I do that. And I think she's sleeping. And then when I start talking through one of these videos, it inspires her to get up and do something. So. All right, gang, anyway, as we saw in the previous video, reliability is just addresses consistency with whatever the test intends to measure. I feel like reliability and consistency are two terms that are interchangeable, and I'm pretty sure from here on out that I will use those interchangeably. Reliability has consequences beyond just what we encounter in education. A butcher is certainly concerned with the consistency of his or her scales. I remember years ago I worked at a grocery store, and the reason I thought of this one, and we had calibrated, well, not we, I hadn't done anything, but the butcher had calibrated the scales incorrectly. And it just so happens that he had calculated the scales incorrectly to where it was consistently overweighting, so they were overcharging the customer, for example, a steak. And it didn't really amount to much. And many times it was only maybe a nickel or a dime that the customer paid more than they should have. But I remember the state of Kentucky didn't think it was a small deal. And in fact, I'm pretty sure the owner of the grocery store got a pretty huge fine on that one. I know he was really, really mad at us. And I don't know, I didn't feel like I did anything wrong because I didn't know anything at that time. Guys, educators, and that's going to be certainly our approach here, is, not only, it's going to be so natural for you guys to think about testing as simply the test that you give in your class to your students, or the test that you take part of this graduate program. And it's natural to do that, and I think most of the things that we study in this reliability and validity part certainly apply to those. But keep the eye on the prize here. We're mostly concerned with how tests are used in education research, and some of you are even kind of interested right now in your. Or at least the previously or even currently, some people who are doing research in our program are interested in measuring things like motivation and situational, dispositional types of things. So, and we call those things constructs. We'll get into more about constructs when we get into validity. But you think about, how do you measure anxiety? It's something that we can certainly see. Sometimes. I even still suffer anxiety, not as much as I used to, but we know when the stakes go up, we get more anxious. But how do you measure that? what kind of instrument could you create to measure something like anxiety or motivation, some of these constructs that are observable, but when you actually try to measure them and use them in education research, it becomes more problematic. So by the time you get through this entire section of reliability, validity testing, measurement, theory, measurement errors, you're going to know more about that. So guys, at the end of the day, in a nutshell, educators, if you're going to use some sort of aptitude test or any type of test, you would want consistency in the results, not only from an ethical perspective, but you would want and need it if you're going to publish your results. So presenting reliability analysis and validity are two important components in education research that deals with instruments and tests. Now, theoretical framework. Reliability is concerned with the effect of errors on the consistency of scores. And there are two types of errors that I want to discuss with you. One is called a random error of measure, and one is called a systematic error of measure. Random error, as you would expect, is an error that is associated with just pure chance. The thing about random errors is they, as I say there in the second bullet, they inflate or deflate in an unpredictable manner. Systematic errors also inflate or deflate a subject score, but they do so in a predictable manner. And I'm going to try to give you some examples of this stuff. So anyway, systematic errors are typically the root of validity problems, and random errors, what we're looking at right now, are the root of reliability problems. Think that'll be a test question? Which is which? Possibly so. Guys, random error. We have three types of random error that leads to inconsistency or low reliability. One is the individual. I don't know. As I'm putting up this video, and I hope to use this in the years to come, so they tell us never to do anything that's like time specific or talk about anything time specific, but I'm going to violate that. As I'm putting up this video, University of Kentucky has a pretty decent basketball team. In fact, I think right now we're 28-0, and I think we are the favorite to win the NCAA. Problem is, the favorite usually doesn't win the NCAA, so that's really got me concerned. But, time will tell. We'll see. But some of my buddies, just flip out, even though we're 28-0. Last night we played a game, and we didn't play so well. And we only beat a team by about 20 points that I felt like we should have probably beaten by about 50. Well, the fact of the matter is, there are certain things that happen with teams in terms of randomness. So when think about the individual or the team, motivation changes from game to game. Motivation changes from a test to a test for a student. Interest, fatigue, so on and so forth. More specific to testing, some people are good guessers, and I'll tell you what, some people aren't good guessers. There's actually a program it's used in a lot of introductory psychology courses. You go to a psychology lab and you take this test. Sorry, I got a text from my secretary who I'd asked to call me. I'll tell you what, hold on just a second. Let me respond to this. Sorry, gang. All right, between the dog and texting. Anyway, I was telling you the story. There's a program that you see a lot in introductory psychology courses that test how good of a guesser that you actually are. And I thought, that's kind of cool because I've always thought I was a really bad guesser. I always feel like if I've got a 50-50 chance, it doesn't seem like I get the correct choice 50% of the time. Seems like it's more than 25% of the time. So anyway, I thought, this is kind of cool. I'll sign up for this test and see whether what I see day in, day out is really kind of theoretically proven. Well, guys, my result on that test of how good a guesser I was is I have no prayer of succeeding in life if it comes down to guessing. I'm a horrible guesser. So now that you know that, I'm sure that you feel like your life is complete. Guys, testing the administration part. A lot of times people depart from standard testing procedures, clearly testing conditions such as heat, light, and especially noise. Noise doesn't bother some students. Those who have attention deficit disorder situations like me, if I'm taking a test and there's noise, I am completely and totally distracted. I think it's the reason I work so well here at home when I'm home alone is I have no distractions other than my dog wanting in and out, and I think that's why I'm more productive here. And guys, instructions and or scoring procedures. I know recently I've given tests to my college level students, and I have a student that'll come up and kind of call me out on the instructions. And typically when they call me out, they're right. The instructions aren't clear, and it just happens that some students are just more critical readers and take things more, I guess, directly than other students. Some people kind of implement inference. They just kind of assume they know what I want and they go with it. Other people more deliberate and want much clearer and clearly scoring procedures. Guys, the instrument, the length of the test, the impact of length on impact of luck and the length of the test. Guys, you got to think about if you give a test that's got only a few items, then the impact of luck is really magnified. Whereas if you've got possibly a 100-point or 100-item test, then the impact of luck is not nearly as severe. A little bit more on random error. What I'm trying to do, I guess I know where we're headed here, and I know that you're going to be bombarded. Once we get into the calculations of this reliability, you're going to be overwhelmed with these tests and stuff that these examples I've come up with education. So from time to time, I'm trying to go through this and come up with things that aren't necessarily math education test instrument related. So I thought about this one, and I actually got this from some textbook, got the idea from a textbook, to have middle school students throw a baseball as far as possible and measure the distance, okay? Well, variation is certainly expected from person to person, from student to student. I play a lot of golf, well, not near as much as I used to since I got involved in this graduate program, but I used to play a lot of golf, and even when I was pretty good and pretty consistent and reliable, the length of my drives were, not necessarily all the same. In fact, depending on the how critical the distance is measured, you might argue that they're never the same. So back to the middle school throwing a baseball. What could explain some variation? Well, they could have a sore arm the second day. After day one, maybe they get some sort of intervention. Son comes home, said, Dad, throwing a baseball today. And the parent takes the son or daughter out back and said, hey, I tell you what, let me teach you a little bit about throwing a baseball. And the second day, their score goes up. That just creates error. Maybe used a different ball from day one to day two, or possibly even a different ball within each day. Weather conditions are something that I came up with that could potentially create some error. Maybe there's different examiners, test administrators on day one and day two. And, clearly sample size would have an issue. 2 days is certainly better than one, but 3 would be better than 2, 4 better than 3, and I promise you I'll stop. Guys, errors and measurement. How does one tell the difference between random and systematic errors? Well, let's think about the baseball. Let's assume the 2 baseballs are being used, and let's say the one is kind of soggy and one is very firm. If the administrator just randomly selects the ball that the student receives, then this is a random error because the ball was selected randomly. This would be a reliability issue. However, let's say that we have again 2 baseballs are being used, and one is soggy, one is firm. But all girls are given the firm ball and all boys are given the soggy ball. Well, this is not a random error. This is systematic. This is a decision that the test giver, the test administrator, has created on his or her own, and it would clearly create systematic error. and this would impact the validity of the test, not necessarily the reliability. I actually have a pretty cool, whoa, back up here, guys. I actually have a pretty cool, it's like a bullseye, and it shows somebody shooting a gun. Maybe it's a little violent, but it shows the difference. Gives you a picture of the difference between reliability and validity as it comes to shooting at the eyeball. So maybe I'll make a copy of that and show it to you in an upcoming video. Well, guys, you probably know what's happening. I'm going to briefly merge reliability and validity. Again, reliability is concerned with consistency. Validity is concerned with the meaning and the interpretations of the scores. Scores can be reliable without being valid. Scores are valid only if they've been shown to be reliable. And a really good way to think about this is at a temperature gauge. A temperature gauge is valid if it actually provides an accurate interpretation of temperature. So if our temperature gauge is valid, then it would have to be reliable from day to day, from hour to hour. But guys, we could have a temperature gauge that is reliable without being valid. For example, let's say our temperature gauge is broken, and it constantly, consistently, there's that word again, measures 5 degrees higher than what it really is outside. Well, our gauge isn't valid because it's not giving us the measurement that represents the phenomena we're trying to measure, but it is certainly reliable. Speaking of, I'm completely and totally convinced that my speedometer on my car, I think it's very reliable, but I don't think it's valid. I don't think it gives me the speed of the car, because I think it's consistently given me a speed that's somewhere about 3 to 4 miles per hour more than what I'm actually traveling. And I don't know if you've ever, I know you have, if you driving down the highway and they have one of these signs, kind of instruments, slow down, and it tells you the speed you're going. And every time I get into one of those, I always I try to mix up things, and I try to do, well, let's go 35, and I want to go 45, let's go 80. And I want to see if I am consistently being over or under measured. And there's, of course, there's some assumptions there that the measuring device, that radar, is actually doing its job. Is it actually valid? So, but anyway, I'm convinced that my speedometer is extremely reliable, because it seems to measure my speed somewhere between 3 and 4 miles per hour higher than what I'm actually going, but it certainly isn't valid. Now, guys, we get into kind of the cool stuff here. When we get into to test theory, there are 3 types of test theory, and we're going to focus primarily on the classical true score model, but there is more modern test theory as well. And I'm not going to get into these in this video, but it is going to be something I'm going to address in future videos. So put on your radar that classical and modern test theory breaks down into 3 types of test theory. Classical true score model, what I call classical test theory, and generalizable theory and item response theory are 2 other, I would say, more recent theories, if you will. Classical truly is, it's a classical true score model. So I want to talk to you a little bit about this classical true score model and what we mean by this, okay? So via an example, when a student gets a 72 on an exam, what do we really know? Well, first of all, we can bring in some new terminology, and we can say that 72 is their observed score. We also know that there's natural variation in testing. So if we had tested the same student at a different time, they most likely would not have scored a 72% because of the random error component. I never will forget, years ago I was invited to ACT in Chicago to actually give a speech on something. It was something actually that I found in my dissertation and in my research. So this would have been back in 2000, I think it was in April 2002, actually, so it's been many years ago. And we were just hanging out at a breakfast before I was to speak, and we were talking about how we can use ACT scores or Compass scores or in-house placement exams to place students. And it came up, for example, let's say we have a test and the cutoff from intermediate algebra to college algebra was 30. So if a student gets a 29, they go into intermediate algebra, which is a 5-hour course at the time. So they have to pay the extra tuition, take all the extra time, whereas a student gets a 30, they get to go on to the 3-hour college algebra course. And we came up with, it came up in the discussion, well, what do you do? Well, I said, well, I would, maybe retest the student, or I'd probably talk to the student. I would probably look at other factors like high school grades. I'd try to get an indication of motivation, attendance, are they going to attend class? These other things that we know have an impact on success in a math class other than just the placement test score. Well, there was this lady, I think she was from Illinois or Indiana, one of the I states, maybe even Iowa. She kind of called me out. She said, well, that's just stupid. If the student gets a 29, then they go into intermediate algebra. If they get a 30, they go into college algebra. And I remember thinking, really, lady, you're too stupid for me to talk to, because that's a really, really crazy conclusion. Because if you look at the 29 and 30, with rounding, we essentially could have had someone who scored a 29.49 and another student who scored a 29.50, 1/100th of a point difference. In theory, this could have happened. And we make a very important decision based on 1/100th of a point, keeping in mind that if the student took the test again, they would very, very, very likely score something different. And I take this into consideration. We all have this or at least we seem to have this threshold of 60% being the determining factor between failing a course and not failing a course. Well, keep in mind that your measurements aren't perfect, and that very, very likely if you'd gone through and regraded your assignments, especially if there's partial credit, there's a good chance that from day in, day out, we assign partial credit differently, especially when you increase the number of levels of partial credit. If you've got 10 points on a particular problem, and you're sitting there trying to decide whether that student gets 0 points, 1.2, 0.3 point, up to 10 points, there's more measurement error there. Whereas if you've only got 3 points, there's less measurement error. So the more points you've got per question, the more that you're going to have fluctuation in the points that you give for the exam over certain days of grading. And guys, this has been proven. This is not, you might say, well, I don't agree with that. I don't care if you agree with it or not. It's been proven that that's the case. And I always say that not for you to reflect on this, but I remember having that same dialogue with myself when I first started. Kind of when I was at this stage of learning, studying test theory and measurement. I remember having the same dialogue, but after I learned more, I softened up that dialogue. So guys, the third bullet down there under the second big one, we have to admit that there's error in measurement that directly implies there's a true score. So the true score might be thought of as the mean if the student took the exam, or an exact alternate form, and we talked about that before, infinitely many times. So really a very, very good way to think about this is an IQ test. What is my IQ? I have no earthly idea, and I have taken 9 IQ tests. And I think I told you this in a previous video, I've yet to get the same score on any of the 9. In fact, there's been a lot of fluctuation. My lowest IQ, my highest IQ, I'm not going to tell you what those were, but I will tell you the variation. There was about 15, 16 points, I don't remember exactly. It seemed like it was, let's see, well, no, actually more than that, about 18, 19 points difference in my lowest and my highest. So there was clearly fluctuation in my IQ scores. So, if I took the IQ test, infinitely many times, which we can speak of in theory, but not empirically, then I would have a overall mean score, and I think that would be a legitimate way to visualize the true score. Well, guys, this brings us to something important. We have to realize that there are two components to this. Well, actually, there are three components. There's the score that we observed. We have to realize that there's an error of measurement because scores fluctuate even from person to person. We know they fluctuate from student to student, but sometimes we don't stop to think that these scores actually fluctuate from person to person. And so we have to think of an observed score, a true score, and an error of measurement. Moreover, the error component may be caused by a number of factors associated with the student, the test environment, and the list goes on. So gang, upside down smiley face, frowny face, whatever it may be, one of the toughest things I had to admit is that my test scores in my classes aren't as perfect as we may have thought. Now, I'll tell you what, back in one of my earlier graduate level courses, and this is going to make some of you smile, I used to grade my assignments on a check minus, a check, and a check plus. You got to let me know if that made you smile. Because, and I came under some fire because that's not typically what people see. People want grades from 0 to 100. We want A, we want to see B, we want to play the education game like we've always played it. I'm not that good. I'm not. I can't figure out exactly when I go through and give partial credit whether you should get an 80 or an 81. I'm not that good. I can't, 91's an A minus, 92 is an A. Guys, I'm not that good. And my argument is I don't think anybody else is either. So I thought, you know what, if I can get this down to a check minus, which day in, day out kind of represents a C, a check, day in, day out represents a B, good work, and a check plus, day in, day out represents a check, excellent work, I am going to be doing cartwheels because I think I have done a hell of a good job in trying to categorize the level of work submitted on the assignment. And I do hope that made you smile. All right, gang, more on classical true score model. The reliability of a test is expressed mathematically as the best estimate of what proportion of the total variance of scores on the test is true variance. So what's true variance? What's random variance? So guys, if we administer a test to a group of students, we encounter two sources of variation. We encounter the variation among the students. Students will certainly vary. Scores will vary from student to student, not always. I've actually had scores with very, very little variation. I don't think I've ever had a class where everyone scored the same. We've all had tests where there's more variation than others. And then there's variation due to errors of measurement, which is more specific to the student. So gang, at the end of the day, the idea is presented mathematically very, very nicely. Some of the stuff we get into later is not going to be presented so nicely, but we can say that the observed score can be expressed as a sum of the true score and the measurement error. So just to give you an idea, let's say that my true IQ is 80, and I go out and take an IQ test and I get a 82. Then my observed score is 2 units higher than my true score, so my measurement error here would be 2 units. Clearly, day in, day out, some of our scores are going to be below our true score. Some of our scores, and if you think about infinitely many test administrations, then half of your observed scores will be above your true score and about half will be below. So gang, true score, got some facts. The true score component will be equal to the observed score under conditions in which a perfect measuring device is used. So if a perfect measuring device is used, or if, first of all, if you think you've got a perfect measuring device, you and I need to talk because you're not going to have it. But if that condition, again, well, I'm speaking theoretically here, if that happens, then your true score and your observed score, your t will be equal to your x, and your e will be equal to 0. Measurement error can be positive or negative, as we talked about before, for reasons also. We can think of the distribution of our errors will be normally distributed, and the sum and obviously the mean. If the sum's 0, the mean obviously has to be 0. So the sum of the errors and the mean of the zeros of the test will be 0. And guys, the true score is a theoretical concept. Again, what is my true score IQ? I don't know. And that brings me back to one of my quotes that I just absolutely love. And I kind of coined it when I started studying. I didn't coin it. I didn't come up with it. I just read it and used it. But Albert Einstein, in one of his later books, before he passed away, somebody asked him, Dr. Einstein, you're clearly a very, very smart guy, and you clearly have had the opportunity to work with a lot of smart people over your lifetime. In your best estimation, your feeling, what is the difference between people who are really, really bright and people who are, let's just say, so-called average intelligence? And he thought, and he came up with a brilliant answer, as you would expect, because it's Einstein. He said, really, at the end of the day, I don't think he said at the end of the day, that's a Darbroism, far overused Darbroism. But at the end of the day, intelligent people say, I don't know, more often. And my students, when I say that in class, they look at me like I'm crazy, because they're like, well, you think that, intelligent people know more answers than average intelligence, and they really do. But I think what he was saying is that you say I don't know more often because the answers to problems are, the more you learn, at least, you find out that they're more sophisticated and complex than just on this just a simple framework that we're used to working with. All right, gang, the research situation. This is what really it's all about. Somebody said it's all about the hokey pokey. Well, no, it's not about the hokey pokey. It's all about the research situation for these. And guys, you can tell when I start getting bored with putting up videos, when I put up too many videos, I start getting slap happy. So please accept my apologies. At least I haven't started playing any Taylor Swift music yet. So the research in a research situation, the researcher doesn't have the capability to test subjects infinitely many times for obvious reasons. And typically in research, we take one measurement on each subject. Now, you might be thinking, I'm a Darbro, and back in quantitative measures, we talked about repeated measures, and we do. But I'm talking about we just take one measurement on the person. We don't sit there and have this infinite number of measurements on each person. So we kind of have to take one measurement, and granted, there may be another measurement taken, days later, and another measurement. But at that particular moment, we can only assume, in research, we only take one of the measurements. So guys, the researcher has a single set of scores to consider, one for each subject. It can be shown mathematically that the variance has a kind of the sum of the components of variance, that the variance of the observed score can be expressed as the sum of the variance between the true score and the measurement error. So that turns out to be an important relationship. And really, if you look at it, it's x equal t plus e in the classical true score model anyway. So we're just saying the variances are equal across those components as it was initially presented. Reliability coefficient. Theoretically, the reliability is thought of as the ratio of the true score variance to the observed score variance. And when I first look at that, I try to think, and when I've got sigma squared t divided by sigma squared x, when I first look at that, I'm like, no, wait a minute, how do we know that the variance in the true score model isn't going to be higher than the observed score? Which gives us a correlation greater than 1, which is problematic. Well, again, you can just look at the partition of the sum of the variances, and you can see that unless there's no variation in the measurement error, then the numerator has to be larger the denominator has to be larger than the numerator. So gang, at the end of the day, reliability is the proportion of variance in the observed score that is free from error. So those are going to be two things that'll pop up a lot in different shapes, forms, and sizes. So gang, putting it all together, the degree of error is indicated by the degree of departure from the reliability coefficient 1. So a reliability coefficient, I should say, of 0.95. My dog wants back in, but oh gosh, she'll be fine. Maybe I need to play her some Taylor Swift or something, some Shake It Up. All right, a coefficient of 0.95 on a test tells us that 95% of the observed variance in the scores is true variance, while 5% is associated to measurement error. So a reliability coefficient of 0.95 is really good. Reliability coefficients near 1 indicate the scores derived from the instrument have little error and high reliability. So again, little error results in high reliability. Significant error results in low reliability. And reliability coefficients quite a bit below 1. You know, what's quite a bit? I have no idea, but let's think about, 0.40, 0.30, 0.50 indicate the scores are derived from an instrument with significant error and low reliability. Now you might say, well, I don't care. I don't care if my instrument has reliability. I don't care if it contains error. I don't care how much error it contains. And I kind of get that. I mean, this is really getting into fine tooth comb stuff. But you have no prayer of getting any sort of research published unless you address, if you're trying to use a test or an instrument without addressing reliability and validity. So guys, back where it all began, a test is reliable to the extent that the scores made by an individual remain nearly the same in repeated measures. There are different ways to do that. We have split half, we have test retest, we have these internal consistencies. But consistency is a measure that is indicated by its standard error of measurement and its reliability coefficient. The standard error of measurement, to me, is the kind of a measurement of reliability across the student, across the individual, across the subject, where reliability coefficient is specific to the test. So, reliability coefficients that we looked previously, and we're going to get into more, are test, retest, equivalent forms, and we can address or examine internal consistency using the following. Cronbach's alpha is the one that... actually, I left something out. There's actually a Cooter-Richardson 20 and a Cooter-Richardson 21. So if you're taking screenshots or taking notes like you should be, make sure you add that. But Cronbach's alpha is the one that I would probably depend on. And I think by far it's the one that's most frequently reported. Well, gang, that is it, as you can tell. So take care.